Okay guys, so I'm making this video on section 2.6, which is on the rational functions, which begins on page 166 of your book if you were absent. Okay, so a rational function is just a function of polynomials that are quotients. So it's going to look like a fraction, all right? The general form is some function is equal to numerator. So you have a polynomial in the numerator and another polynomial in the denominator. And the important thing is that we cannot divide by 0, so you can never have 0 in the denominator. Okay, you'll see some examples in a minute. Okay, the first thing we want to find is the domain. Okay, the set of all x values that the function can take on. So in other words, what values of x can I plug in and not have a problem like 0 in the denominator? So the simplest of all, the thing to do is take the denominator of your rational function, whatever it is, set it equal to 0 and solve for x. The domain is going to include all the values of x except for the result that you get when you solve. Okay, so for example, the simplest function is the function 1 over x. If I take what's in the denominator and set it equal to 0, there's nothing to do. It's x equals to 0. So the domain is going to be all real values of x. So remember, we're not using complex numbers anymore. We're working in the reals. So it's going to be all real values of x except for x equals to 0. Now you can write that in interval notation, which would go from, so in other words, you know, if you think of putting that 0 on a number line, okay, that's going to divide the number line into two partitions. To the left, it's going to go from negative infinity to 0, and to the right of 0, it's going to go from 0 to infinity. We cannot include 0 because if I plug a 0 in here, I'm going to have 1 divided by 0, which is very bad. So you can write this in interval notation. You can say that you know, this function I can plug in a 1, a 2, a negative 10, a negative 50, a positive 100, whatever I want to, just not 0. So in interval notation, you would say it goes from negative infinity to 0, and because 0 is not included, we use a parenthesis, okay, this rounded thing here, in union with, and then you start where you left off here, so from 0 to positive infinity. I can plug any number in except for that one, so those should match. If you want to use set notation, you can say that the domain is the set of all x. This bar right here just means such that x cannot equal to 0. Okay, so x can be anything except for 0. Another example is this one here, 2x plus 1 over x plus 1. Well, if I take the denominator, which I did, x plus 1, and set it equal to 0 right here and solve, I'm going to get x equals to negative 1. Right? To get x by itself, I have to subtract 1 from both sides, so I get x equals negative 1. So what I know is that the domain can be any real number except for x equals to negative 1. Now you can write it like this. The reals is this double barred r, like that. So that's what this is. The reals except x equals negative 1. You could say, you know, again, if you want to think about putting negative 1 on a number line, you're going to have from negative infinity to negative 1 and negative 1 to positive infinity. So you could write it in interval notation, just like that, in union with negative 1 to infinity. And again, we're using parentheses because negative 1 is not included. Or you could use set notation and say the set of all x such that x cannot equal negative 1. Okay? The next example, I have to factor a little bit. I have to realize that the denominator here is the difference of two perfect squares. So if I factor this denominator, I get x plus 1 times x minus 1. So I have to set each one of those factors equals to 0, which I did here, and solved, and I got x equals to plus or minus 1. So the domain is the set of all reals except plus or minus 1. You can write it this way. If they want interval notation, again, you know, think of your number line. Now you would have a negative 1 and a positive 1. So that's going to split your number line into 3 pieces, right, or 3 partitions. You're going to have from negative infinity to negative 1, from negative 1 to 1, and from 1 to positive infinity. So essentially, if you can think like that, all you really have to do for set notation, or sorry, interval notation, is put a union in between them, okay, like I did right here. Or you could say the set of all x such that x cannot equal plus or minus 1 would be equivalent. Okay? The second thing we need to talk about for these rational functions is vertical asymptotes. It's going to be the line x equals some number. So you're going to solve for it the same way you did for the domain. You're going to set the denominator equal to 0 and you're going to solve for x. So there's no difference, okay? And a vertical asymptote is going to be a vertical line, and because it's a line without a slope, it's going to be x equals some number, okay? And the vertical asymptotes again are going to be those x values that make the denominator 0. So if we look at this thing on a graph, you're going to see like jumps in the graph. And I forgot to get my calculator, so let me go grab that real quick. And also asymptotes, whether they're vertical or horizontal or slant, a graph's going to always get really, really, really close to those asymptotes, but it's never going to cross or touch those asymptotes. So let me get my calculator very quickly. Okay, all right, so a simple example is the one we just did, this function 2x plus 1 over x plus 1. If I want to find the vertical asymptotes, I just take what's in the denominator, set it equal to 0, and solve for x. So x equals -1, and you know, if you were to graph this, which we're going to do eventually in a little bit, on the coordinate plane at -1, you would have a vertical line at x equals -1, meaning that the graph's not going to cross or jump that, cross or touch that. And just to show you, I'm going to go ahead and put this function in my calculator. Right, so that function is 2x plus 1 divided by x plus 1. Okay, and I'm going to hit the graph key. So we expect to see some jump of the graph at x equals -1. And lo and behold, it may be kind of hard to see here, but at -1, this right here, if you think of a vertical line, in fact, let me put one there. Second, draw vertical. And I'm just going to put a vertical line right about there. You can see, I'm going to just move my cursor out of the way, that the graph gets really, really close to those vertical lines from the left and the right. But it looks like it touches, but it doesn't. It's my vertical line is not quite at 1. It's hard to actually put it right at -1 or something like that. Okay, so anyway, the graph's going to get really, really close. It's going to hug those asymptotes, but it's not going to cross. Here's another one, 4 over x squared plus 1. Now here's the kicker on this. If I take that denominator and solve, I get x squared equals -1. And if I try to take the square root of a -1, that's a complex result, right? The number that I'm going to get out of that is a complex number. So the key is that, you know, if that happens, then there are going to be no vertical asymptotes because they have to be real numbers. And the other thing you can think about when you look at a denominator, you know, no matter what I plug into x squared or in for x, I'm going to square it. So if I put a -1 in here and I square it, it's going to become a +1. So 1 plus 1 is 2. So no matter what, even if I plug a 0 in here, 0 plus 1 is 1. No matter what I plug in here for x, I'm never going to have 0 in the denominator, so I'm not going to have any vertical asymptotes. Another situation you might find is where, you know, you've got this binomial with some multiplicity here in the denominator, such as x minus 1 squared. Well, I want you to know that that's just x minus 1 times x minus 1. So when you solve, you're going to get the same x equals 1 solution. So you only need to do it once. Just look inside the parentheses and set that equal to 0 and solve. And so we know we're going to have a vertical asymptote at x equals to +1, and there's my little dotted line there. Now again, if I put this in my calculator, so let me do that. So it's going to be 2 divided by x minus 1 quantity squared. So I just went ahead and threw that in the calculator. And if I hit the graph key, I would expect to x equals to 1. See, the graph's getting really, really close to x equals 1 there, but it's not going to touch. Okay? And one more, because oftentimes you're going to have to factor both the numerator and denominator. So I factored the numerator, I factored the denominator. Nothing cancels. Well, all right, let me say this. I have this factor and this factor are common. So for right now, in its present state, this indicates a hole in the graph at x equals -2. You're going to use the sign opposite the one you see. So if you have a common factor top and bottom that match exactly, if you set it equal to 0 and solve, then that means you're going to have a hole in the graph at x equals +2. Now, in this case anyway, or at that factor. I'm going to put this into the calculator to show you something. Oops. Okay, so I put the function in the calculator just as I see it. Notice I've got parentheses in the top and the bottom, and that's for PEMDAS, so that way, you know, just to be on the safe side, I'm not dividing the whole numerator just by x squared or something like that. So it's a PEMDAS thing. But anyhow, if I graph it, you know, I told you I would expect to see a hole at x equals -2. But, you know, if I look at x equals -2, I don't see a hole. I mean, it looks like, I'll zoom in a little bit more. There doesn't appear to be a hole at all at x equals to -2. All right, so the graph is deceiving. But if you go second graph key and you look at x equals -2, you see there's an error there. There's no y value. And that's because there's a hole in the graph. Now, you see another error down here at 3, and I'll talk about that in a second. All right, so first and foremost, we have a hole here. So the domain would be all values of x except 3 and -2 in its current state. If I want to remove the hole, I can cancel those. And that's called a removable discontinuity. Removable discontinuity is the same thing as a hole. But we use, this is the formal math term, and this is the simplistic term. Okay, so what I know is if I just look at the denominator, we're talking about vertical asymptotes, so I don't want to get too far off the ball here. If I take each one of those factors and I set them equal to 0, I expect a vertical asymptote at -2 and at 3, and I drew those there. Okay, and again from this graph, sorry about that, I just hit my camera. If I look at this graph here, x squared minus x minus 6, you notice I don't see a vertical asymptote at x equals to -2. And that's because there's a hole there and it's removed based on this thing. Okay, based on canceling it out or removing the hole, the discontinuity. But in general, if we were going to leave this thing alone, then we would definitely have these two asymptotes. Okay, so just keep that in mind. Once we remove it, we get rid of this one and we only have this one left. I'll try and find another example. Then there's horizontal asymptotes, and this is something you've got to just memorize. They're really, really easy. But horizontal lines are lines that go in this direction, right? Like the horizon, like where the sun sets. And that's going to be the line, or represented by the line y equals some number. So vertical is x equals some number, and horizontal is y equals some number. And this is what you have to memorize right here. If the degree of the numerator is less than the degree of the denominator, then you will have a horizontal, so horizontal asymptote HA, I abbreviated, at y equals to 0, which is just the x-axis. If the degree of the numerator is bigger than the degree of the denominator, then you will have no horizontal asymptotes. And if the degrees are equal in the numerator and the denominator, then the horizontal asymptote is going to be the ratio of leading coefficients. So let's have a look at what all that means. In this first example, we have the graph 1 over x. The degree of the numerator, you can think of this as 1 times x to the 0. and down here the degree is 1. So the degree of the numerator is less than the degree of the denominator, so I can expect to have a horizontal asymptote at the line y equals to 0, which is the x-axis. Okay? In other words, my graph's going to get really, really close, but it's not going to touch. And that's a very basic function, so I'm just going to go ahead and put it in my calculator, 1 divided by x, so you can see, there it is, right? And if I hit the graph key, you can see that, you know, as we're heading toward positive infinity, the graph's getting really, really, really close to 0. And as we're heading toward negative infinity, it's getting really, really close to 0. So this line right here, the x-axis, is the horizontal asymptote. In another one, this is one of the other functions we worked on a minute ago, 2x plus 1 over x plus 1. Notice the degree of the numerator is 1 and the degree of the denominator is 1. They're the same. So the leading coefficient is the coefficient, the number, that's multiplied to the highest power of x. So on top, the highest power of x, and the only one, is x to the 1. We just don't write the 1. On the bottom, there's no number there, so that means there's a 1 there. That automatically means there's a 1. So the ratio of leading coefficients would be 2 divided by 1. So I wrote that over here. We're going to have a horizontal asymptote at y equals 2 divided by 1, or the line y equals to 2. And you just go up 2 units on the y-axis and draw a horizontal dotted line, and you've got your horizontal asymptote there. And again, you know, if I put this into my calculator as 2x plus 1 divided by x plus 1. Okay, so there's the function, so you can see it. If I hit graph, then what you can see is there goes the graph, and I'm going to insert a horizontal line, and I'm going to just bring it up to about 2, so 1.95, it's a little more than 2 here, it's 2.07, because again, this is just to, it's hard to get it exact, or at least I don't know how to. But as you can see, the graph going toward positive infinity is getting really, really close to that horizontal asymptote, and the graph going toward negative infinity is getting really, really close. But again, it looks like it, but they don't touch or cross that asymptote. Another one would be something like 3x squared over 2x minus 1. The degree of the numerator is 2, the degree of the denominator is 1. That means the degree of the numerator is greater than the degree of the denominator, so I wouldn't have any horizontal asymptotes. And if I put that in the calculator for you to see, so there's the function, and I hit the graph key, you're going to see that there's definitely no horizontal line that this graph is hugging. Okay, so there's not going to be a horizontal asymptote. And finally, trickery. Sometimes they'll write the function out of order, so it's not, you know, 3x squared minus x minus 4, which is fine. But again, what you want to look for is the highest degree of the numerator, the highest power of x on top, and the highest power of x down the bottom. Scan it from left to right. These are the same, so that means I'm going to have a horizontal asymptote at the ratio of the leading coefficients, which is negative 3 over 7. Okay, and 3/7 is somewhere between, negative 3/7 is somewhere between 0 and negative 1. And so I would draw my little dotted line at about negative 3/7. Remember that 7 over 7 equals 1. So anyway, there it is. Okay, it's good enough. Y-intercepts. If you want to find a y-intercept, remember all of these f of x's, you can just change that to y equals if you want to. But if you want to find the place where the graph crosses the y-axis, because that's what a y-intercept is, then you plug a 0 in for the x in the function, and whatever's left over is what y equals. So the first example, 3 over x minus 2. If I let x equal to 0, then y should be some number. If I plug a 0 in for x, that's 3 over 0 minus 2. Right, so I wrote it out here. Normally I wouldn't write that out. So when x is 0, what is y? It's 3 over negative 2, or negative 3/2. In the second case, if I plug 0 in for x, I'm going to have 0 over negative 2, which 0 divided by anything is 0, so when x is 0, so is y. Here's another case that's similar. If I plug a 0 in for x, I have 0 over 0 plus 4, which is 0 over 4, or 0. So when x is 0, y is 0. These are points, remember, coordinate points, x, y coordinate in the plane. And then something like this, if I plug a 0 in for x, well, that goes away, so I'm left with 1 over negative 3, or negative 1/3. So when x is 0, y is negative 1/3. And that's the place on the graph that's the place where the graph is going to cross the y-axis, is at the y-intercept. The x-intercept is the place where the graph is going to cross the x-axis, okay? So that's going to happen when y is equal to 0, because everywhere along the x-axis, y equals to 0, okay? You know, think about it. Let me move this over a little bit. When x is 0, y is 0. When x is 1, y is 0. When x is 2, y is 0. When x is negative 2, y is 0. When x is negative 3, y is 0. So anywhere along the x-axis, y is equal to 0. So I want to know where my graph's going to cross the x-axis, or intercept it. Okay? So it's always going to be some number. It could be 0, but some number, comma 0. This will always be 0 when you're looking for the x-intercept. And with a rational expression, it's easy, because all you have to do is take what's in the numerator and set it equal to 0 and solve. So in this first case, we've got a rational function. I set the top equal to 0, the numerator equal to 0, dividing both sides by 5, I get x equals to 0. So the graph's going to cross the x-axis at the point 0, 0. When y is 0, x is 0. Okay. Another one here. So look, you know, this is y equals, but I could put the 0 here if you want to. I just put it to the right because a lot of students like that better. I'm going to take what's in the numerator, set it equal to 0, and solve. I subtract 3 from both sides to move it over to the right-hand side. Divide both sides by negative 7. Negative 3 divided by negative 7 results in a positive 3/7. So when y is 0, x is 3/7, and that's the place where the graph's going to cross the x-axis at the point 3, 7, comma 0. And finally, the last case, this one's a little bit more complex, but again, it doesn't matter. I'm going to take what's on top, I'm going to set it equal to 0, and I'm going to solve. And doing so, I get x squared is equal to 1/4. So when I take the square root of both sides of this, don't forget your plus and minus. This is the square root of 1 over the square root of 4. The square root of 1 is always 1, and the square root of 4, as you know, is always 2. So it's going to be plus or minus 1/2. So I know the graph's going to cross the x-axis at negative 1/2, 0, and positive 1/2, 0. Then we have something called slant or oblique asymptotes. These two words mean the same thing. They're asymptotes that are slanted. Okay, it's going to happen if and only if the degree of the numerator is exactly 1 more than the degree of the denominator. And slant asymptotes are the equations of lines. They're linear equations of the form ax plus b, where a is the slope of that line. And to find a slant asymptote, you have to use long division. All right, and I say over here, discard the remainder. You can discard the remainder because as the graph starts to hug the slant asymptotes, the remainder goes to 0. It's insignificant. So we want to focus on the linear part of the function, and that's going to give us the slant asymptote. So for example, I have this function here, this rational function, x squared minus x over x plus 1. So I went ahead, it's always top divided by bottom, right? So this is my divisor, this is my dividend here, so the top always goes in the box, right, in the divisor box. And I divided. I said x goes into x squared how many times? X. So x times x is positive x squared, but we've got to change the sign so we can cancel that out. And x times 1 is a positive x, but we change the sign to a negative. So when I combine these, the signs are the same. I get negative 2x, and now I start again. X goes into negative 2x negative 2 times, Negative 2 times x is negative 2x, but I changed the sign to a positive. And negative 2 times 1 is a negative 2, but I need to change that to a positive 2. Now this is going to be the remainder, right? I can't do any more. X doesn't go into a number. So at this point I stop and I say that my slant asymptote is the line y equals x minus 2. It's whatever is up here, okay? So to plot that, you plot the y-intercept first, which is the point, when x is 0, y is negative 2, so I plotted that first. And then I'm going to use rise over run. Well, the slope of this thing is 1 over 1, so I went up 1 and over 1 and plotted a second point and just drew a dotted line through it. That's my slant asymptote. Now in this one, I also notice I have a vertical asymptote at x equals to negative 1, so I drew that as well, because you're going to have to draw all asymptotes, horizontal, vertical, and whatnot. And by the way, in this one here, the degree of the numerator is bigger than the degree of the denominator, and so I'm not going to have any horizontal asymptotes if I were to graph this particular function. Okay? And you can tell on the calculator when you're going to have slant asymptotes. I mean, you can tell just by looking that the degree here is 1 more than this. But if you put that into the calculator, divided by x plus 1. So I'm putting the function into the calculator so you can see. And if I hit the graph key, you're going to see these graphs. You notice the line that I had for the slant asymptote was what? X minus 2. Right? So the y-intercept's down here, so it's going something like this, my slant asymptote, sort of like that. I wish I had something thinner. Maybe this pencil. Well, I'll use this ruler. So here's my line, the ruler line. The light's glaring there. Anyway, the slant asymptote goes like that, and you can see that the graph of the function just hugs that asymptote. Okay, so what you're going to do is, using all of this information, you're going to learn how to sketch these by hand in just a minute. Here's another one. F of x equals x squared plus 5 over x. Now, just looking at this thing, what I notice is I don't have any horizontal asymptotes, right? There's no horizontal asymptotes because the degree of the numerator is bigger than the degree of the denominator. The other thing I notice is I got a vertical asymptote at the line x equals 0, right, the y-axis, because I can't plug a 0 in here and have 0 in the denominator. And then I know I'm going to have a slant asymptote because the degree of the numerator is exactly 1 more than the degree of the denominator. So to find that equation, I need to divide. And I don't want you to forget that it's x divided by, now this goes x squared plus 5, so you're going to remember to fill in 0, x to the whatever is missing in between, right? It has to go in descending order, so squared to the first power to no power at all, or the constant. All right, so I went ahead and I did that, and I said x goes into x squared x times x is positive x squared, change the sign, those cancel. All right, and then I brought down my 0x and my plus 5. X goes into 0x 0 times. So at that point I'm done. So the line, or the equation for my slant asymptote, is the line y equals x, which is just this line right here. Okay. Here's another example. Again, I'm missing the x term in between, so I had to fill in a 0x here. I did some division and I got the line y equals to x minus 1. I also noticed I'm going to have a vertical asymptote at x equals to negative 1, so I went ahead and put both of them on there. Here's my slant asymptote and here's my asymptote. So this brings us to, I can find x-intercepts, y-intercepts, horizontal, vertical, slant asymptotes. I can find the domain of a rational function. By now you should all be able to factor with ease, because you had so much factoring in Algebra 2, that now we can sketch these without a calculator. And the steps are like so. If you want to sketch a rational function, first try to simplify the numerator and denominator if you can. You're not always able to, but if you can, factor out the function and simplify it. Step 2, find and plot the x and y intercepts. Okay, let x equal 0, let y equal 0, and plot those. Sketch the horizontal, vertical, and slant asymptotes. plot a point between and beyond each of the x-intercepts and the vertical asymptotes. So you'll see more of what I mean when I do one. And then connect those with a smooth line. So let's do an example. I'm going to take one out of the book. Hi, Ella. My dog is wondering, what am I doing? I'm not playing with you, huh? So let's see. I'm going to do number 55 from the book. So this is going to be number 55. From page 176. And here's the function. Function is f of x is equal to x cubed over x squared minus 4. Okay, so the first step was to simplify this function if I can, right? So I can't simplify the numerator, but I can simplify the denominator. I see that this is a difference of 2 perfect squares, so I can write this as x plus 2 times x minus 2. And that's helpful because right away, you know, I can see my vertical asymptotes are going to occur